Hello wonderful person, this is Anton, and today we're going to be discussing a somewhat intriguing discovery of a very special type of a supernova. A type of a supernova that technically was hypothetical for a very long time, but that scientists have now definitively witnessed with the image you see right here. And though normally in astronomy, when we talk about the life and death of stars, we usually talk about massive stars basically exploding and turning into a black hole or a neutron star, today we're going to discuss this star that seems to have completely deleted itself from the universe. It essentially left nothing behind. And so in this video we're going to discuss this new study by Daiichi Hiramatsu and a team you see on the screen that released a study describing this incredibly rare event that we often refer to as pair instability supernova. The event's so rare and so powerful that it literally vaporizes the entire star, scattering every single atom into outer space. And so let's discuss the discovery of this cosmic giant in a bit more detail, explaining the strange physics behind this phenomenon, and talk about why this discovery changes what we know about the early universe. But first, let's start with the initial discovery from October of 2023. And as with many supernova, this was the result of the automated survey referred to as ZTF, Zwicky Transient Facility. The automated telescope that essentially tries to catch as many of these events as possible by observing sudden shifts in brightness in all locations it observes. And the vast majority of recent supernova were all discovered using this telescope. And so in this case it spotted a new dot, a dot of light, in a tiny faint galaxy approximately 1.3 billion light years away from us. And at first, astronomers assumed that this was a typical Type II supernova, where essentially a giant star explodes and leaves behind a black hole or sometimes a neutron star. So basically a typical massive star core collapse. But as they watched it, the data in this case started to look kind of incorrect. And that's because usually these explosions brighten quickly and then fade over time. But SN 2023 VBW really took its time. First, it rose steadily in brightness for approximately 190 days, which by the way is an incredibly long time for a typical supernova. In other words, we've never actually seen supernova take so long to reach their peak, but then it also released a staggering amount of energy equivalent to 3 × 10 to the power of 50 ergs, or just to give you a slightly different comparison, approximately 10 times more explosive than any supernova we usually observe. So whatever was happening here was already quite strange. With the additional clue coming from the environment where this happened. This was in a dwarf galaxy with very low metallicity, or basically a small galaxy that's not particularly developed and very likely contains a lot of ancient stuff. So mostly hydrogen and helium, not a lot of heavier elements. And in these environments, usually stars can actually grow pretty large and pretty massive, and on average tend to produce much more powerful supernova and much bigger explosions. That's actually because they don't really lose as much mass through stellar winds, and are thus just a little bit less active, making them eventually explode with a lot more mass. But that still did not explain why the explosion was so powerful, which takes us to this next theoretical proposition in regards to what's known as pair instability supernova. And so in order to understand this, we have to take a look at the internal pressure of the star. And for many decades, astronomers believed that some of the most extremely massive low metallicity stars end up creating such unique conditions inside that the final explosion when they do go supernova basically completely rips them apart. And so in a normal massive star, like for example Betelgeuse, the push that keeps the star from collapsing usually comes from the gamma rays, or the extremely high energy light, produced by the core's nuclear furnace. But as the star gets more massive, and as the pressure and heat inside increases, and especially if the star reaches approximately 130 solar masses, the core becomes so ridiculously hot that properties inside change so much that the physics become different. And specifically, the gamma rays become so energetic that through the Einstein's famous E = mc², these gamma rays, or this energy, starts to transform back into mass. Or basically all of this energy produced by the nuclear fusion inside the star then transforms back into matter because of these ridiculous pressures and temperatures on the inside. And specifically, it starts to create pairs of electrons and positrons, and like a lot of them all over the place. And that creates a bit of a problem for the massive star. Normally, these gamma rays are supposed to create the outwards pressure, preventing the star from collapsing. But matter doesn't do that, and instead of pushing everything from within, these electrons and positrons actually now add just a little bit more mass and start to pull things into the star with even more gravity. And so suddenly the star finds itself lacking that internal push that was preventing it from collapsing and from destroying itself. This is of course the instability part. And usually this is referred to as pair instability because it basically involves a pair of subatomic particles. And so we now have a star whose outer layers suddenly lose their support and start to crash inwards faster and faster and faster. With this collapse causing the core to heat up even more, reduce the gamma rays even more, produce even more electrons and positrons, and basically triggering a kind of a runaway thermonuclear explosion that happens so suddenly and becomes so violent that it doesn't just blow off the outer layers like in a typical supernova, but it consumes the entire star all at once. There's literally nothing left behind, no leftover core, and nothing to form into a black hole or a neutron star like during a typical event. I guess you could call this a celestial eradication. And for a very long time, this was actually one of the main propositions when it comes to black holes, and specifically why we don't really see black holes of certain masses. And that's because only stars below 130 solar masses should be capable of producing black holes, and these stars will only produce black holes with certain masses. But since more massive stars just explode completely, they're not going to be creating black holes and will actually create what's now referred to as a black hole mass gap. But intriguingly, some of the recent discoveries from gravitational wave surveys started to find black holes that seem to defy these rules, and right now this does not have a very good explanation. You can learn more about this in some of the videos in the description. Although intriguingly, if the star becomes even more massive, over approximately 250 solar masses, something entirely different seems to happen too. Here, instead of a core collapse, and instead of a nuclear explosion, these stars go through something referred to as photodissociation. In this case, the energy from the light inside break down the atomic nuclei absorbing the energy, and the energy then drains away, causing the star to just directly collapse into a black hole and basically produce no explosion, which is literally almost the opposite of the pair instability supernova. And that type of an event was also possibly witnessed, and I think there should be a video in the description talking about that as well. But back to what's happened here. And so, do we actually have a lot of evidence that this was indeed a pair instability supernova? Well, first of all, the study suggests that the star that caused this was probably some kind of a massive blue supergiant. So actually something very similar to what we see in the Homunculus Nebula, that seems to contain a very powerful, very massive star inside that's already gone through some very strange transformation. But in this case, 2023 VBW seems to have also produced the ejecta estimated to be about 170 to maybe 350 solar masses. In other words, when it exploded, it seems to have released at least 170 solar masses in terms of mass of different types of gas, which is very similar to the mass predicted by these pair instability supernova models. And in this case, it also seems to compare to this other peculiar supernova from approximately 12 years ago that was also a little bit difficult to explain, because this star seems to have gone through multiple eruptions and also created a very unique light curve that we've never seen before. And though for this particular supernova, even today it's not entirely clear how to classify it, this seems to fit the pair instability theory pretty well. Here in the data, there's even evidence for something referred to as circumstellar interaction, or basically after the star exploded, the fast-moving debris started to slam into a disc-like shell of gas that used to exist around the star, with the interaction providing extra heat and extra light, which is basically visible as these unusual bumps in the data. And based on this research and this observation, it looks like this is the best candidate so far for this previously hypothetical and theoretical proposition. In other words, the data from this explosion seems to directly match everything predicted in a lot of these pair instability supernova models, which is of course a very important confirmation for the mystery of this black hole mass gap. Or basically the stars of certain mass, between 130 and 250 solar masses, will always destroy themselves completely, and that means that we should not be finding any black holes with masses in a certain range. For black holes, this mass would be anywhere between 50 to 130 solar masses. And the thing is, since some black holes have been found to have these masses, it has now been suggested that there's a very high chance they were produced by merging with something else previously. Once again, the video in the description talks about this a little bit more. And so generally speaking, when we find these black holes in this gap, it just tells us that something else must have happened here, and they must have merged multiple times. But on top of this explosion and this theory also helps us understand how certain elements seem to have formed. And that's because these explosions and these pair instability supernova are predicted to produce massive amounts of heavy elements like silicon and iron, with many of these elements eventually being recycled into new stars and eventually into planets and, of course, people. So basically, by studying the supernova and by seeing the exact process and the exact evolution, we're going to learn so much more about how the universe is enriched in these elements and how some of the stuff inside of us was very likely formed. And lastly, this is also something that scientists believe must have happened to some of the first stars in the universe, the mysterious population 3 stars. Or basically, when some of the first stars in the universe started to be created, they very likely were extremely massive, possibly even thousands of solar masses, and were all made out of hydrogen and helium and pretty much nothing else. And those stars also very likely exploded over time, but most likely left nothing behind, creating these very powerful emissions and enriching everything around them with a lot of heavier elements. But since we cannot actually easily see these first stars, right now this supernova is our best local laboratory to understand how the universe's first stars lived and died. Because in some sense, this star resembles them quite a lot. But obviously, because this is a scientific study, right now the evidence is still not super conclusive. In other words, this is just the first study about this, and we do need to hear about confirmations. So basically, there are still certain uncertainties, and this could still be something else. But in this case, the team behind the study notes that additional telescopes like the Vera Rubin Observatory should be actually seeing a lot more of these events and will potentially find tens or even hundreds of these every single year. And so instead of being 1 in a billion kind of a rarity, we instead might soon see a huge catalog of these pair instability events and thus understand them just a little bit better. Although here this is also a reminder that even the most massive and the most powerful objects in the entire universe are still temporary, and their total destruction is exactly what makes our existence on Earth possible. So basically, if it wasn't for these explosions billions of years ago, you and I would not exist. On that note, once we learn something else, we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.